First off, we must appreciate that not all gels are created equal. Some gels can be more economical or easier to use, while others may be necessary depending on your targets. Gels can be prepared in the lab or purchased commercially. Pouring your own gel can be cost-effective and allow you to optimize depending on your targets by changing gel chemistry, acrylamide percentage, well number, and gel thickness. On the downside, pouring your own gels can be troublesome and hazardous. Gel pouring systems can leak, which can lead to running artifacts and can increase your variability from experiment to experiment. Also, gel components including acrylamide are toxic, so appropriate protective equipment should be used when preparing acrylamide solutions. Purchasing precast gels can be more expensive, but can save time and reduce gel-to-gel variability. Nowadays, there are many options where you can select gel chemistry and acrylamide concentration depending on your targets. Precast gels can also help standardize your workflow and allow for better reproducibility. Acrylamide is used in the gel to act as a molecular sieve to help separate proteins by molecular weight. The distribution of acrylamide in the gel can either be homogeneous or as a gradient. Resolving gels with a single percentage of acrylamide are easier to prepare, but need to be adjusted depending on your targets. Low percentage acrylamide gels, between 6 to 8%, are ideal for separating high molecular weight proteins. On the other hand, high percentage gels, roughly 12% acrylamide, are ideal for separating low molecular weight proteins. Gradient gels can be helpful when the molecular weight of your protein is unknown or if you're detecting multiple targets with varying molecular weights. Gradient gels varying from 4 to 20% can resolve proteins with molecular weights from about 10 to 200 kilodaltons. When it comes time to run your own gels, you will need to choose the appropriate gel for your targets and your application. The Tris glycine system is commonly used for most Western blot applications, as the components are relatively cheap and can be used for a wide range of proteins. But you might think about using an alternative buffering system or gel composition depending on your targets. For example, the Tris acetate gels are ideal for high molecular weight proteins, while Tris tricine gels are ideal for low molecular weight proteins and peptides. The gel running buffer provides sufficient electrolytes to conduct the flow of electrical current. In the Tris glycine system, running buffer with a pH of 8.3 forces glycine ions into the gel, forming the trailing ions, which are critical for the migration of your proteins. Other gel systems require different running buffers, so make sure that your running buffer is compatible with your gel system. Now that we've learned about the different types of gels, you can choose the one that is most appropriate for your targets.